Hello students, welcome to class 11. I know that it is a pretty unusual way for you to start your plus 2 given the present circumstances. Your ISC exams are suspended, your schools are suspended, you don't have the books with you, so the situation is a pretty difficult one. It is not something with which we can deal with pretty easily, but again, because the syllabus for class 11 and 12 is so vast, we cannot wait for a pretty long time, and it is just that we start the syllabus, we start the topics one by one right now. Now if you look into the syllabus in the council's website, you should find that dimensional analysis, which we are going to do today, is one of the topics in your syllabus. It is among the first things that you are going to do in class 11. So let us start with the proceedings. So what is this dimensional analysis and what are we going to study in this chapter? Now these are the 7 fundamental quantities with which you are already aware. You studied this in class 8 or 9, that in physics there are 7 physical quantities which are the fundamental quantities. By fundamental, we mean that they cannot be derived from anything more fundamental. They are like the building blocks. And from these fundamental physical quantities, we can get a lot of other derived quantities. So the 7 fundamental quantities are written here, like length, which is measured in meter. There are also a lot of other units for length, but meter is the SI unit. Similarly for mass, the SI unit is kilograms. For absolute temperature, the SI unit is Kelvin. For time, it is second. For electric current, it is ampere. For luminous intensity, it is candela. And for the amount of substance, it is mole. And then there are the derived quantities like velocity, which is meter per second, or density, which is kilogram per meter cube. So those are the derived quantities. So these are the basic 7 fundamental quantities, and you are already aware of it. Now what is new that we are going to do today? The thing is, what is the framework beneath this? Like for example, when I write that the unit of velocity what are the different units that you can write for velocity? In the SI unit, it's obviously meter per second. You can also write kilometer per hour. That's right as well. If you go to the FPS system, which is used by the British, then it is foot per second, or rather plural, so feet per second. That is again a correct unit. You can also even write kilometer per minute. You can write meter per hour. These are various units. Now we are more familiar with the first unit because that is the SI unit and that have been used widely. But that does not imply that these units are wrong. So if there are so many different units just for velocity alone, how can we connect them all? And here comes dimensions. So if you look at them all, they have the same dimension. And what is that dimension? Dimension of length to the power 1 and dimension of time to the power -1. Here capital L represents the dimension of length. So length has got the power 1 in all of this. Whether it's meter or kilometer, feet, the highest power is 1. Similarly, capital T represents the dimension of time. And again, the dimension of time here, the unit time has got the power -1 in all of this. So this is more like a general framework, something that's acceptable globally, no matter which unit you are using. Similarly, if you look at something like density, it can again be expressed in various units. The unit we are familiar with is kilograms per meter cube because this is the SI unit, but we can also write it as grams per centimeter cube. We can also write it as pounds per feet cube, which is in the FPS system. But once again, the underlying universality is there. It is the dimension of mass to the power 1 and dimension of length to the power minus 3. By dimension we mean that in place of length we can place any unit we want, in place of mass we can place any unit we want. Mass and length, they are like the building blocks, much like the skeleton. So it can be skeleton of a dog, it can be skeleton of a cow, it can be skeleton of a human and so on. But all these skeletons, they are made up of the bones, they are made up of the same constituent of calcium. But how the muscles, how the various organs, how the various nerves they develop, how they exhibit themselves, that would lead to the final product as to whether the creature will be a dog or a cow or a human and so on. So it's much like this. This is the basic framework beneath them. Now in your book you shall find that the first definition that they have given is that the dimensions of a physical quantity, the dimensions, that is these ones, are the powers to which the fundamental units are raised in order to obtain the derived unit of that quantity. So this portion is important. The powers to which the fundamental units are raised. Whenever we are talking of dimensional analysis, we will only deal with the fundamental units, that is these 7 units. We shall try to represent all the derived quantities in terms of these 7 units only, the fundamental units only. Let us give some example. So let us take another derived quantity, force. What is the SI unit of force? It's Newton, and Newton is basically kg meter per second square. So kg is the unit of mass, so it's dimension of mass to the power 1 multiplied with meter, that is dimension of length to the power 1 multiplied with second, that is dimension of time to the power minus 2. So this is the dimensional formula of force. Let us take another example. Let us consider Q, which is charge. Charge is equal to current multiplied with time, because current is charge per unit time. So this is equal to dimension of current, which is ampere to the power 1, and dimension of time to the power 1. So you see, once again, when we are writing this, we are taking the dimensional formula only. You can express your time in seconds or minutes, you can express it in hours, but still the formula remains the same. So this is basically the basic framework that comes into play when we are dealing with the dimensional formulas. Alright, now if you look into your syllabus for class 11, it says under dimensional analysis that you need to know the dimensional formula, you need to express the derived units in terms of base units, which we just did. Newton was a derived unit, we expressed it in form of base units. The principle of homogeneity of dimension, we shall be doing it, expressions in terms of SI base units, and then using the dimensional analysis to check whether the equation is dimensionally correct, to obtain the dimensional formula of any derived physical quantity, and to convert units from one system to another. So these are the applications that we are going to do. So the first application says to convert units from one system to units of another. First application says to convert units from one system to another. Fine. So What does it mean? Suppose you have something like 100 kilograms. I want to know that in the unit of gram, what will be the value. Now this is a pretty easy one because you know 1 kg is 1000 gram. But in other units, or if this particular unit on this sites, there's something which we are not familiar with, then it can be pretty difficult to find it out directly. So for that reason we use the dimensional analysis. So what does dimensional analysis say? Say we are measuring any physical quantity P. That physical quantity can be written as N1 times the dimension of that physical quantity, which is expressed as U1 within brackets. So if I for example consider force can be written as the value, that is 10, and the unit, that is Newton. Or if I am taking acceleration can be say written 20 times the unit, that is meter per second square, and so on. So any physical quantity, it can be expressed as its value, which is the magnitude multiplied with the unit. In some other system, it can be written as some other value times some other unit. We can easily write that. Now for this physical system, physical quantity, for the first case, N1 U1, how can we write it? It is say N1, and then U1 was the unit. Now whatever be the unit, it can always be expressed in terms of the fundamental quantities. So I can write U1 is some, suppose, mass to the power A, then length to the power B, and time to the power C. I don't know what is the value of A, B and C. They can be positive, negative or 0. It doesn't matter. Similarly, there can be another physical system of units in which I am representing this physical quantity, that is N2 U2. In that case, this will be N2, then M1. This is a different system of units, so M2 to the power A, L2 to the power B, and T2 to the power C. Now look here, we are trying to write the physical quantity in general terms. So we need to understand this. First of all, N1 and N2, these are the values, like 100, 10, 50, 20, these are the values. They don't have units. Values are like magnitudes. Magnitudes don't have units. And these are the units. Now the units, I am taking to different system of units. I don't know whether this is kilogram or feet, whether this is grams or pounds. It's unknown to me. That is why this is M1 and this is M2. This is L1 and L2. They may be equal, they may not be equal. For example, the length in both the systems can be meter, but it may be so that this is meter and this is kilometer. Or the time can again be same in both the cases, but it may be so that this time is second and this time is minute. So in order that we do not lose generality, we have taken T1 and T2, the separate ones. That is the best possible general case. And if you look at the powers are A, B, C for both of them. The powers remain the same. Why? As I had told in the initial part of this video, that whether whatever system you are using, powers remain the same. If you are measuring velocity meter per second, then also power of length is 1 and power of time is -1. And if you are measuring in kilometer per hour, then also the power of length is 1 and power of time is -1. So the powers does not change, because that is the basis of dimension, to what power you are raising the fundamental quantities. Therefore I can take the variables A, B and C to be same. Now ultimately both of these represent the physical quantity P. So they are equal to each other. That is to say, N1 U1 is equal to N2 U2. So that can be written as N1, the dimensional formula, is equal to N2 we can write it like this. Therefore, if I make N2 to be the subject, N2 is N1 times M1 divided by M2 to the power A, L1 by L2 to the power B, and T1 by T2 to the power C. This is the general manner in which we can convert one system of units into another. When we will do an example for this kind, it will be even more clear to you.